you're asking what is the integral of a function f over a curve? Okay, so that's a very good question too. So remember, we also talked about, when we talked about line integrals, there were two types of line integrals, right? There were line integrals of vector fields and line integrals of functions. And then line integrals of functions was kind of, it's like one of those cousins nobody wants to talk about, right? So it's like it's there somewhere, but suddenly we don't talk about them anymore, right? But actually, because the reason is, it is very useful, those integrals are very useful, but those integrals are not as easy to fit in this formula, so to speak. But since you asked me, those were, strictly speaking, those were not exactly integrals of functions. We kind of thought of them as integrals of functions, but we never wrote integral of f, right? We never wrote integral of f. And this doesn't make sense unless you integrate over points. For example, here you can think of this as an integral over 2 points of a function, which would be just evaluating 1 point minus evaluating the other. We never write this as an integral over a curve, or over a two-dimensional domain for that matter. Over a curve, we can only integrate f ds. Or you have to put some measure here. You have to put ds or dx or dy, something like this, right? So ds is actually also a differential form. It's a kind of object like dx and dy, and I spent some time about a week ago talking about this, right? So you have to remember this. And if you treat this not as an integral of a function, but integral of this expression, right, then it actually fits into this general theory. Okay? Yes? Where did it come from? It was just, well, for example, when we go from a function to its differential, right? It's just, that's the way it is. That's a formula which gives you the formula for the differential involves partial derivative with respect to x dx plus the same for y, right? The formula was explained before because this was the formula for the linear approximation of the function, right? Now we are developing a formalism which allows us to relate integrals over domains and their boundaries, right? And it turns out that within that formalism, there's a certain procedure which you have to make, starting with an object on the right-hand side, to get the object on the left-hand side. And we have now seen two examples of this in action. This is the first example, which was last week. Here you actually have a function, and on the left then you have to take its differential. And now is a new example. Here we start with a vector field with components p and q, and then that's this expression. But if I had just written this expression without any explanation, you would say, what does it mean? How did you get this formula? I have tried to give you an explanation of that formula in a way which also makes it parallel and similar and analogous to this formula. Okay, well, let's move on now and do a few examples of this. As you can imagine, this actually has some very important applications, because you can now trade an integral on one side of this formula for an integral on the other side. And oftentimes, one of these integrals is very complicated and maybe not even possible to evaluate easily, and the other one may be very easy to evaluate. Okay? And so that's what we're going to try. That's what we're going to do, and this is how we're going to apply this material, apply this formula. So here's an example. Suppose that your curve C is a boundary of a parallelogram like this. This is your curve C, and it will be positively oriented, which means that you go counterclockwise. Okay? This is your curve C. And suppose you're asked to evaluate the line integral over C of the following expression: x e to the minus 2x, x e to the minus 2x dx plus x cubed plus 2x squared y squared dy. Okay? So this is exactly the kind of expression that I'm talking about in this formula, in Green's theorem. You have general expression is p dx plus q dy. But as I already explained, in order to apply Green's theorem, you have to make sure that the curve over which you integrate here is closed, has no boundary, right? So let's see, can we actually have a chance to apply Green's theorem to this line integral? For this, we have to make sure that the boundary of this curve is empty. Is it empty? Yes, it is empty. It is a closed curve. So we're in good shape. We can actually replace it by the left-hand side of Green's theorem. Why would you want to do this? Well, someone might say, I'll just calculate this like this, and to which I would say good luck. Because see, first of all, you have to break it into 4 parts. You have to integrate over each of the segments. Each of the segments you have to parameterize. Once you parameterize, you have to substitute parameterization here, and then go and find the antiderivatives of those functions. Okay, maybe in this case it's not so bad, but I could have written something much more complicated, obviously, for which you wouldn't be able to find the antiderivative. Which I will on the exam, right? And that will be the first indication for you to know that you shouldn't do it in a straightforward way. You should not do it directly. It's just way too complicated. Okay? So you think of other ways to evaluate this. And here it is beneficial to use Green's theorem. What does Green's theorem tell me? It tells me that this is equal to the double integral over the interior of this curve, which is the parallelogram itself. This is D. Of what? I have to take, let me write it here. I have to take dq dx minus dp dy. And what are the p and q? This is p, right? And this is q. So let's take the derivative of q with respect to x. I get 3x squared, right, plus 4x y squared. And now I have to take also the dp dy. And p is this. And lo and behold, p actually does not depend on y at all. It only depends on x. You see? So we kind of lucked out here. This complicated looking function will actually disappear when we go to the other side of Green's theorem, because this actually will be 0. This is 0. So I don't have to add anything to this. In general, I have to take dp dy. But dp dy is 0. Right? Everybody agrees with that? dp dy is 0. It does not depend on y. Its partial derivative with respect to y is 0. So this is already simplification. So you can imagine, here is the quickest exercise that you can give to somebody, but kind of, which looks complicated, but actually the easiest to calculate. That would be if I actually wrote here something which only depends on y. Let's suppose that I give you a formula here, right? I wrote here a very, very complicated function, but only depending on y. I would write some square root of 1 plus e to the sine y or something. And then you look at it, so it really looks horrible. But then you apply Green's theorem, and you see that dq dx actually is 0. No matter how complicated the function would be in y, if it doesn't depend on x, this would be 0. And then this would be 0, and this would be 0, and the answer would be 0. So you don't have to calculate anything. So you already see the power of this method, that sometimes you get the answer right away, even though the original integral looks very complicated. well, this would be sort of a gimmick. If I give you this, it would be sort of a gimmick. You'd be saying, okay, so it's just, just playing with that. But this is sort of a more serious example, right? Which is kind of intermediate level, where one of the functions disappears and the other one does not disappear. So you actually have to calculate something meaningful. You have to calculate this, of course, dx dy, or dA if you want. So now we have to remember what we learned about double integrals. You have a question? Right. So the question is, do I have to put dx dy, or I can put? There are two issues here with dx dy. Okay. So in this discussion of this procedure, you have to keep track of this, and that is a discussion which goes into the issue of the meaning of the formulas. So it's kind of a fundamental stuff about deriving these formulas, right? This is one aspect of it. Another aspect of this is when we do double integrals, we treat them as iterated integrals, where we first integrate over one of the two variables and then we integrate over the second variable. Both of them are okay. They don't introduce any sign. The switching that I'm talking about is the switching in the formula when you pass from here to here. But once you're doing a double integral, you can do it in either way. You see what I mean? So don't worry about it. The sign only happens in this discussion, so it's to explain why there's a minus here and there's no minus here. But when you're actually doing the double integral of an expression like this, the rules which we have used to evaluate these integrals, and those rules involve integrating over x and then over y, or over y and then over x. Also, this rules will give you the same answer. Okay. So let's actually evaluate. So you have, you know. So let's say, so this is going to be, now we do it as an iterated integral. And you choose, as I said, you can choose whichever you like for the first variable and whichever you like the second variable. So let me see, let me say do here y from 0 to 2, and there here the x will be from 0 to 5, and then I will have 3x squared plus 4x y squared, here I have dx, and then I'll have dy. Right? So here you will have x cubed, right, plus 2x squared y squared from 5 to 0, which is, what's 5 cubed? 1.5, right, plus 50y squared. Right? Tell me if I'm making a mistake somewhere. And then you do the outer integral. I'm doing this because I'm trying to remind you, because this is something we haven't done since, I guess, since the exam. So I hope you haven't forgotten. We certainly have to use this knowledge, right, in this discussion. So 125 plus 50y squared dy. And that's going to be 125y plus 25 plus 50 over 3 y cubed, 2 and 0. So you have 250 plus 50 over 3 times 8. Okay, whatever. So this is how you compute it. Yes?
So that answer represents the line integral over that first cube of your
That's right. So this is a very easy way to calculate what would have been a nightmare calculation if you had approached it in the most direct way, right? This is the answer for the integral of this vector field over this curve. Now, we are lucky here. I want to emphasize it one more time. This is something which we cannot apply to a general line integral. We can only apply it to a line integral over a curve like this, which has no boundary. If my question was to calculate over this segment, or even over this, or even over this, something which has a boundary, I would not be able to do this. Of course, what I could have done, say, if the integral was like this, I would say, okay, I'm missing this part. But if this part were there, it would be this. So let me say that this then is equal to this part minus this integral. So I would be able to trade this integral over 3 segments for a double integral plus or minus the integral over 1 segment. So in other words, not everything is lost, even if your curve is not bounded. It is not closed. You could trade a complicated curve for an easy curve also. But here we're actually lucky because the curve is closed, so we just trade the single integral, line integral for double integral, which is much simpler to calculate. Yes. I'm sorry? Does what look like a square? Does this curve look like a square? Does it have to look like a square? First of all, it looks like a parallelogram, not a square, right? At least I meant it to have unequal sides. But a curve, to answer your question, let's do another example where the curve is not a square, or a parallelogram for that matter. Let's do another example. Suppose that your domain, you have to evaluate a line integral of something which has 2 components. So I would like to draw a picture like this. Okay? So I would like to say that here, again, I can use Green's theorem. This is equal to p dx plus q dy. But where the region, my 2-dimensional region, will be the annulus, which is confined between these 2 circles. The first circle, let's say, would have radius 1, and the second circle will have radius 2. Okay? In all the previous discussion, I assumed that my region, so to speak, didn't have holes. In other words, the boundary consists of only a single curve. And now this region sort of has a hole in here, right? So the boundary now consists of 2 circles. There's an outer circle and there's an inner circle. But it turns out that Green's theorem is applicable to such regions as well. But you have to be very careful with the way you put orientation on the boundary. The orientation on the exterior circle, we have already figured out, is counterclockwise. And that's going to stay the same in all cases. But now the question is, which orientation you should put on the inner circle? Clockwise, exactly. Because see, this is exactly a situation where the counterclockwise rule doesn't apply. Counterclockwise rule only applies to the exterior boundary. But for the inner boundaries, it's going to be the opposite. It's going to be clockwise. And the reason is that the universal rule involves this. You have to think of a person walking here. And if you walk, and the domain has to be always on your left. So that means that you have to walk counterclockwise outside. But if you go counterclockwise on the inner circle, on your left will not be the domain, but will be something else. Right? So you have to walk like this, like this here. I'm not doing that one, but like this here to have the domain on the left. So, which brings us to the second example, in which let's say you have some function. Oh, where did I put it? Oh yes, here it is. Brings me to the second example where, let's say you have the following concrete functions. So let's say this C now represents the union of both of these boundary curves, right? Taking with the appropriate orientation. And so let's say you're evaluating the following thing. You have cosine x dx plus x squared sine y dy. So this is P and this is Q. Right? So we use Green's theorem, and Green's theorem tells us that this is going to be an integral over this annulus of dq, again, dq dx minus dp dy, which is 2x sine y minus dp dy. So again, I chose the function to be such that actually this disappears to make it easier. Okay. And now I need to evaluate this double integral. And of course, here you have to remember all the tricks which you learned in dealing with double integrals. When you do double integrals, you have this entire toolbox available to you. You don't have to do it in a straightforward way, first x and y. You can, for example, use polar coordinates. And surely this region calls for polar coordinates. Right? So what you need to do is you need to switch to polar coordinates, and the integral that you will get will be as follows. You will have 0 to 2 pi and over theta, and then from 1 to 2, I recall that this has radius 1, this has radius 2. So theta you integrate from 0 to 2 pi, but r you integrate from r to 2, and then you substitute the polar coordinates, so you get 2r cosine theta, right? And then you have sine of r sine theta, right? And then you have r dr d theta. Q dx. Maybe I made it too complicated. Let me just get rid of this. It's just for the sake of practice. So let's just get it to. I think it's good enough. Okay. And then but don't forget to put an extra r in dA. So then you have this extra r dr d theta. And then of course this you can already do very easily. Okay. So we'll continue on Thursday.